Hello everyone. Today we will be discussing about different types of products of subaerial weathering and the process of submarine weathering and their products. So far we have discussed different types of subaerial weathering that includes physical weathering and chemical weathering. Now let's look into the product of subaerial weathering. We have already discussed about different type of subaerial weathering, and let's now talk about the products of subaerial weathering. There are basically three types of weathering products produced due to subaerial weathering, which are important to the formation of sedimentary rock. The first one of these is source rock residue, which consists of chemically resistant minerals and rock fragments derived particularly from siliceous rocks such as granite, rhyolite, gneiss and schist. The second component of the weathering product is the secondary minerals, which were formed in situ by the chemical recombination and recrystallization, which are basically formed as a result of hydrolysis and oxidation. And the third component is soluble constituents released from the parent rock, mainly by the chemical weathering process such as hydrolysis and solution. These are the three types of weathering product formed as a result of subaerial weathering. Until all these products are removed by erosion, the residues and secondary minerals accumulate at the weathering site to form a mantle of soil composed of particles of various composition and grain sizes ranging from clay to gravel. So those are the particles of clastic nature that are formed as a result of weathering. The grain size and composition depends upon the grain size and composition of the parent rock, upon the nature and intensity of the weathering process. So the nature and intensity of the weathering process and the parent rock composition governs the grain size and composition of the weathering products. So if you look into the source rock residue, that was the first type of product of subaerial weathering, in which the young immature soil developed as a result of weathering of igneous or metamorphic rocks that include, in addition to the rock fragments, some mineral assemblages with low chemical stability. The example for which is biotite, pyroxene, hornblende and calcic plagioclase. If you remember, you must have noticed in our Gordic weathering series, you have found that pyroxenes, hornblende and biotite, those are the minerals that were unstable under weathering conditions. So from that you will be able to understand these minerals are assemblages found in immature soils. Now let's look into the mature soil. If you recollect the same Gordic weathering series, you must be remembering that the minerals, those are most stable at the weathering environment were quartz, muscovite and some potassium feldspar. So the mature soils developed after more prolonged or intensive weathering that commonly contain more stable minerals such as quartz, muscovite and potassium feldspar as we have mentioned. Weathering of limestone by solution produces thin soil composed of fine size insoluble silicate and iron oxide residue of these rocks. Now let's go into the secondary minerals. Secondary minerals developed at the weathering site are dominantly clay minerals, iron oxide or hydroxide and aluminium hydroxides. Those are the secondary minerals developed at the weathering site. The common secondary iron minerals include goethite, limonite and hematite. Clay minerals formed in immature soils under only moderately intense chemical weathering condition may be illite or smectite. Now let's look into the intense weathering condition where the leaching leads to the formation of kaolinite. And let's look into the extremely intense chemical weathering condition. You will have aluminum hydroxide such as gibbsite and diaspora formed. These later clay minerals are also called as aluminium ores. Now let's look into the soluble material that are formed as a result of subaerial weathering, which are basically extracted from barren rock by chemical weathering process and are removed from the weathering site in either surface waters or soil groundwater, and this process is happening continuously from the inception of the chemical weathering process. Ultimately, these soluble products make their way into rivers and are carried into the ultimate sea ocean. The most abundant inorganic constituents of rivers, which represents the principal soluble products of weathering, are, with the decreasing order of their abundance, are basically bicarbonate, calcium, silicic acid, then sulfate, chlorine, sodium, magnesium and potassium. These constituents are the raw material from which chemically and biochemically deposited rocks such as limestone and cherts are formed in the ocean. Now let's discuss about a process called submarine weathering, and also let's look what are the products of such a submarine weathering process. Submarine weathering process is an important kind of weathering that take place on the ocean floor. Sediments and rocks on the seafloor are altered by reaction with seafloor. This process is known as hydrolysis or submarine weathering. Hydrolysis include alteration of clay minerals of one type to another, leading to the formation of glauconite from feldspar and mica, and formation of philipsite, which is a zeolite mineral, and paragonite, which is basically altered volcanic glass from the volcanic ash. Dissolution of the siliceous and calcareous test of organisms, which is nothing but the shell of the organisms, may also be considered a type of submarine weathering process. The seafloor shows evidences of submarine weathering of basalts, particularly on the mid-oceanic ridges, which results in the hydration and leaching of basalts as well as changes in composition of seawater. What happens is, because of the submarine weathering of basalts, it causes ion exchange during the reaction of seawater with the rock. The low temperature alteration takes place as seawater percolates through the fractures and voids in the upper part of the ocean crust, which perhaps extending to up to a depth of 2 to 5 kilometers. Olivine and interstitial glass in basalts are replaced by clay minerals like smectite, and further alteration may lead to the formation of zeolite minerals and chloride. As a result of these changes, chemical elements are exchanged between rock and water, and large volume of seawater become fixed in the oceanic crust within the hydrous clay minerals and zeolites. Alteration of oceanic rocks occur both at low temperature, which is less than 20 degrees Celsius, and at higher temperatures ranging up to 350 degrees Celsius. Whereas when you see the large scale hydrothermal activity which takes place in the ocean, the example for which is submarine thermal springs along the Galapagos Rift. Hot springs occur along mid-oceanic ridges in both the Pacific and Atlantic Oceans, as well as along convergent plate margins, in back arc basin, and even on mid-plate volcanoes as in Hawaiian chain. These hot springs originate where the seawater enters the ocean crust along the fractures or other voids, as we have mentioned, and comes in contact with the hot volcanic rock. So what happens? The water heated up and flows out into the ocean through the vents on the ocean floor and mixes with the overlying water. So the heated water rises as hydrothermal plumes up to about 100 to 300 meter, or sometimes even it goes up to 1000 meter above the vent field. So if you may see the same process in the figure that is shown in the slide, it is basically a multiple orifice black smoker that I will be discussing shortly, that is found in Mothra hydrothermal vent field. So if you see at the sites of many oceanic hot springs, investigators have found spectacular vents composed of sulfide, sulfate and oxide deposit up to 10 meter or more tall, and the discharge plumes of hot solution as we have mentioned previously. These vents or chimneys are also known as black smokers if they discharge water containing suspended fine-grained dark colored minerals, or else they will be called as white smokers if the water contains no suspended dark minerals. If dark minerals present, then we call it as black smokers, or else we call it as white smokers. The temperature of the water when it emerges from the vents may exceed 350 degrees Celsius. When this hot solution mixes with the seawater of ambient temperature, they precipitate various minerals, especially pyrite and chalcopyrite, to build sulfide deposit around the vents. Now, the reaction between hot basalt and seawater play a major role in regulating the chemical composition of the seawater. The magnesium, sulfate and sodium ions are removed from the seawater during this exchange, whereas many other elements such as calcium, iron, magnesium, silicon, potassium, lithium and strontium are enriched in the seawater. The entire ocean, what happens is apparently circulate through the ocean floor hydrothermal system on a time scale 10 to the power 6 to 10 to the power 7 years. So over this period of time, the whole water in the ocean circulate through such a ocean floor hydrothermal systems. So what is the important is this has a significant impact on the budget of several elements including silica in the ocean water. Both seafloor hydrothermal reactions and continental weathering process supply ions to the oceans that is used either by the organism or extracted in the form of chemically deposited rocks such as limestone or iron-rich sedimentary rocks and cherts. So these are the product of submarine weathering. So with this we complete the chapter on weathering. So far we have learned two types of weathering, that is subaerial weathering and submarine weathering process. In subaerial weathering process we have learned physical weathering and chemical weathering, and we have also seen the products of submarine weathering and the process of submarine weathering of the basaltic rock. Thank you.